Hi, this is Vikram Narayanan. I will be presenting our work, RedLeaf, a new operating system built to explore language-based isolation. This is a joint work by University of California at Irvine and VMware Research. 4 decades ago, early operating system designs identified the ability to isolate kernel subsystems as a critical mechanism for increasing the security and reliability of the entire system. Unfortunately, despite many attempts to introduce fine-grained isolation to the kernel, as shown on the graph, modern systems remain monolithic. Historically, software and hardware mechanisms remain prohibitively expensive for isolation of subsystems with tight performance budgets. Focusing on performance, modern commodity CPUs provide only basic support for coarse-grained isolation. Hardware isolation mechanisms are rather expensive, and the overhead of safe languages are prohibitive as it typically involves a managed runtime and a garbage collection. However, with Rust, the balance of isolation and performance is changing, making Rust arguably the first practical language that achieves safety without garbage collection. In a traditional garbage collected language, we have a pointer A pointing to a vector. By passing references, multiple pointers can point into the same object, forming aliases. After the objects are deallocated, the garbage collection needs to walk the heap to find out if there are any more aliases and whether it's safe to deallocate the object. However, in Rust, if an object is passed to another scope, the ownership of the object is passed as well, eliminating the need for garbage collection. Rust combines an old idea of linear types with pragmatic language design. Rust enforces type and memory safety through a restricted ownership model, allowing only one unique reference to each live object in memory. This allows statically tracking the lifetime of the object and deallocating it without a garbage collector, and the runtime overhead of the language is limited to bounds checking. With no garbage collection, Rust enables practical language safety, allowing us to run fast device drivers. Language safety, in turn, can enable practical fine-grained isolation of subsystems. Unfortunately, recent projects mostly use Rust as a drop-in replacement for C. However, the true benefits of language safety lie in the possibility to enable practical, lightweight, fine-grained isolation and a range of mechanisms such as fault isolation, transparent device driver recovery, safe kernel extensions, fine-grained capability-based access control, and so on. We built a system using Rust to explore the impact of language safety for fine-grained isolation. However, isolation is hard to achieve. Despite multiple projects exploring isolation in language-based systems, providing a practical implementation remains challenging. In general, safe languages provide mechanisms to control access to the fields of individual objects and protect pointers. For example, here, the objects defined in domain bar cannot be accessed by domain foo unless it is explicitly passed to domain foo. However, when there is a crash after the objects are passed, the objects are potentially left in a corrupted state. To protect the execution of the entire system, the kernel needs a mechanism that isolates faults, that is, provide a way to terminate a faulting or misbehaving computation in such a way that it leaves the system in a clean state. Fault isolation is challenging in the face of semantically rich interfaces. Frequent exchange of references implies that a crash of a single component leaves the entire system in a corrupted state. One can mediate all cross-domain accesses to ensure that objects are deep copied, as shown in this example. When a caller domain crashes, the callee would still have access to the copied object. However, the downside is it imposes overhead as whole hierarchy of objects needs to be replicated. Another mechanism is to introduce a special capability object that wraps the interface of the original object shared across isolated subsystems or reference count the object. Whenever there's a crash, capabilities can be revoked and eventually garbage collected, preventing future accesses by returning an exception. The downside is, after a crash in the domain, the system would still be in an inconsistent state as the capability is revoked in the middle of a computation. Singularity introduced a new fault isolation model built around statically enforced ownership discipline. In Singularity, applications use isolated private heaps and special exchange heap for shared objects. Singularity enforced single ownership model for objects allocated on the Exchange heap. That is, only one domain could have a reference to an object on the shared heap at a time. When a reference to an object was passed across domains, the ownership of the object was moved between domains. When the moved object was tried to access again by the caller domain, it is rejected by the compiler. Singularity developed a collection of novel static analysis and verification techniques enforcing this property statically in a garbage collected sing-sharp language. Single ownership was key for a clean and practical fault isolation model. Crashing domains were not able to affect the rest of the system or leave the shared objects in an inconsistent state. Moreover, single ownership allows secure isolation in a zero-copy manner. Our work develops principles and mechanisms of fault isolation in a safe language. We introduce an abstraction of a language-based isolation domain that serves as a unit of information hiding and fault isolation. We do not use any hardware-based isolation and rely completely on language safety for isolation, because we want to build a system that uses fine-grained isolation as a first-class citizen. RedLeaf is structured as a microkernel system that relies on lightweight language-based domains for isolation. The microkernel is responsible for managing threads, memory, interrupts, and scheduling. A collection of isolated domains implement device drivers, personality of an operating system, that is the POSIX interface, and user applications. RedLeaf domains provide support for fault isolation. We define fault isolation as follows. After a domain crash, first, we can unwind all threads running inside the crashing domain to the domain entry point and return an error to the caller. Second, subsequent attempts to invoke the domain return errors but do not violate safety guarantees or result in panics. Third, all resources of the crash domain can be safely deallocated. That is, other domains do not hold references into the heap of the crashed domain, and we can reclaim all resources owned by the crashing domain. Finally, threads in other domains continue execution and can continue accessing objects that were allocated by the crashed domain but were moved to other domains before the crash. We enforce heap isolation as an invariant across domains. That is, domains never hold pointers into private heaps of other domains. Heap isolation is key for termination and unloading of crashing domains. Since no other domains hold pointers into the private heap of a crashing domain, it is safe to deallocate the entire heap. To enable cross-domain communication, we introduced a shared special heap that allows allocation of objects that can be exchanged between domains. We construct a special type remote reference or RF that allocates a value of type T on the shared heap. However, objects allocated on the shared heap are subject to the following rule. They can be composed only of exchangeable types. Exchangeable types enforce the invariant that objects on the shared heap cannot have pointers into private or shared heaps, but can have RFs to other objects allocated in the shared heap. Users can define their own types on the shared heap. Our ideal compiler validates the interface of a domain and ensures that this particular type does not have pointers pointing outside of the shared heap. In RedLeaf, RFs can be freely passed between domains. We allow RFs to be moved or borrowed immutably. However, we implement an ownership discipline for RFs that is enforced on cross-domain invocations. Ownership tracking allows us to safely deallocate objects on shared heap owned by a crashing domain. The metadata section of RF keeps track of the owner domain and the number of times it was borrowed immutably on cross-domain invocation. Initially, RF is owned by the domain that allocates the reference. If the reference is moved to another domain in a cross-domain call, we change the owner identifier inside the RF, moving ownership from one domain to another. Thanks to Rust's ownership discipline, the caller loses access to the object. All cross-domain invocations are mediated by trusted proxies. If the reference is borrowed immutably in a cross-domain call, we increment the borrow counter that tracks the number of times RF was borrowed. These mechanisms allow us to implement end-to-end zero-copy mechanism in a transparent manner. Ownership tracking allows us to deallocate objects that are currently owned by the crashing domain. We maintain a global registry of all allocated RFs. When a domain panics, we walk through the registry and deallocate all references that are owned by the crashing domain. We defer deallocation if RF was borrowed until the borrow count drops to 0. To enforce fault isolation, RedLeaf relies on invocation proxies to interpose on all cross-domain invocations. A proxy object exposes an interface identical to the interface it mediates. Hence, the proxy interposition is transparent to the user of the interface. Proxy checks if the domain is alive before performing the invocation. It also creates a lightweight continuation that captures the state of the thread right before the cross-domain invocation. The continuation allows us to unwind the execution of the thread and return an error to the caller in case of a failure. To keep the system extensible, we allow domain developers to define their own interfaces, and the domain interfaces are validated by our ideal compiler. The ideal compiler is also responsible for generation of proxy code required for enforcing the ownership discipline on the shared heap. To implement an abstraction of an interface, we rely on Rust's traits. Domains connect to the rest of the system and establish communication with other domains by exchanging references to trait objects. By implementing these mechanisms, RedLeaf enables isolation of domains in our system. Using this, we also built a POSIX interface of an operating system called RV6, which is based on UNIX version 6. This isolation would enable us to implement other powerful mechanisms like device driver recovery. Lightweight isolation mechanisms and clean domain interfaces allow us to implement transparent device recovery with shadow drivers. Similar to proxy objects, the shadow driver wraps the interface of the device driver and exposes an identical interface. Proxies are relatively simple and can be generated from the ideal definition, but the shadow driver is intelligent as it implements a driver-specific protocol. The shadow driver interposes on all communication with the driver. During normal operation, the shadow passes all calls to the real device driver, but it also saves all the information required for recovery of the driver, example, a PCI interface. If the driver crashes, the shadow driver receives an error from the proxy domain. Instead of returning an error to its caller, the shadow triggers the domain recovery protocol. It creates a new driver domain and replaces its initialization protocol. Since the isolation is lightweight, passing through another domain does not impose a huge overhead. Now it's time to evaluate and understand the overheads of language-based isolation. Our system setup consists of two Intel Xeon CPUs. All RedLeaf experiments are performed on bare metal hardware. Though RedLeaf supports symmetric multiprocessing, in our experiments we limit it to single core operation. First, to understand the benefits of language-based isolation over traditional hardware mechanisms, we compare RedLeaf's cross-domain calls with other synchronous IPC mechanisms. SCL4 implements the fastest synchronous IPC across several modern microkernels, on which a cross-domain invocation costs 834 cycles. On an EPT-based isolation framework with VM-Func, a call-reply invocation takes 396 cycles. In RedLeaf, a cross-domain call is initiated by invoking the trait object provided by the proxy domain. The proxy creates continuation to unwind the thread in case the invocation fails and invokes the trait of the callee domain. A null cross-domain invocation via a proxy object introduces an overhead of 124 cycles. Passing one RF adds an overhead of 17 cycles as RF is moved between domains. When shadow domains are involved, it takes 279 cycles for a cross-domain invocation. Memory safety guarantees of Rust come at a cost. In addition to the checks required to ensure safety at runtime, some Rust abstractions have non-zero runtime cost, example types that implement interior mutability, option types, etc. To measure the overheads introduced by Rust language itself, we develop a simple hash table that uses an open addressing scheme and relies on FNV hashing function with linear probing to store 8-byte keys and 8-byte values. Using the same hashing logic, we developed three implementations. In plain C, in idiomatic Rust, that is the style encouraged by Rust programming manual, and C-style Rust, that essentially uses C programming idioms but in Rust. Specifically, in C-style Rust, we avoid using higher order functions and the option type that we utilize in idiomatic Rust code to distinguish between occupied and unoccupied entries in the table. Without the option type, we benefit from a tight cache-aligned representation of the key value pairs in memory to avoid additional cache misses in C-style Rust. We vary the number of entries in the hash table from 2 power 12 to 2 power 26 and keep the hash table at 75% load. We plot the cycle time for each operation normalized to plain C version. On most of the hash table sizes, our implementation in idiomatic Rust remains 25% slower than the one in plain C, whereas C-style Rust performs more or less equal to plain C. One of the critical assumptions behind RedLeaf is that Rust's safety is practical for the development of fast subsystems of a modern operating system kernel. To find out, we developed two high-performance device drivers, Ixgbe and NVMe. We evaluate it on multiple configurations. First, as a RedLeaf driver, where the benchmark application is linked statically with the driver. This is similar to a DPDK application. As a RedLeaf domain, where the application runs in a separate domain but accesses the driver domain directly through a proxy. This configuration mimics if multiple domains want to use the driver domain in a multiplexed setting. As a RV6 domain, when the application runs as an RV6 program, it first enters the RV6 kernel with a system call and then calls into the driver. This is similar to a typical user application in a commodity operating system, which accesses the network stack through the kernel. Finally, we run the last two configurations with shadow enabled. These two configurations evaluate the overheads of transparent device driver recovery. For Ixgbe benchmark, we send and receive 64-byte packets and measure the performance on two batch sizes, 1 and 32 packets. On packet transmit and receive tests, Linux achieves 0.89 million packets per second due to its generic network stack and synchronous socket interface. On a batch of 1, DPDK is 7% faster than RedLeaf for both TX and RX paths. On a batch of 32 packets, both drivers achieve the line rate of 10 Gbps interface. The overhead of additional domain crossings is apparent on a batch size of 1, where the throughput drops with additional domains. With 2 domain crossings, the performance drops by 60% compared to DPDK. However, we are still faster than Linux by 3 times. With batching, the overhead of domain crossings disappear as all configurations saturate the device. To understand the performance overheads of safety and isolation on application workloads, we developed several applications that traditionally depend on a fast data plane of the operating system kernel, a Maglev load balancer, a network-attached key value store, and a minimal web server. Maglev is a load balancer developed by Google. Processing a packet involves either a lookup or insert into the flow tracking table. To compare RedLeaf's performance, we developed the core Maglev logic in both C and Rust. Running as a Linux program, Maglev is limited to 1 million packets per second per core due to the synchronous socket interface of Linux. Operating on a batch of 32 packets, the DPDK version is capable of achieving 9.7 million packets per second, whereas our RedLeaf driver incurs a 25% drop in performance, but everything is implemented in safe Rust. Performance drops with additional domain crossings. However, even with shadow driver recovery and fine-grained isolation, we are 5x faster than Linux's performance. The performance overheads of language-based isolation is thus practical for workloads that really has only a budget of few hundred cycles. This really makes it possible to build a truly decomposed driver with higher security and reliability guarantees. Our key value store relies on a hash table that uses open addressing scheme with linear probing and FNV hash function. In our experiments, we compared the performance of two implementations, a C version developed for DPDK and a Rust version that executes in the same domain with the driver. We evaluate two hash table sizes, 1 million and 16 million entries, with 3 sets of key value pairs at 75% load. The RedLeaf version is implemented in a C-style Rust code, that is, we avoid Rust abstractions that have runtime overhead. This gives us control over the memory layout of the key value pair and avoid additional cache misses. Despite our optimizations, RedLeaf achieves only 61 to 86% performance of the CDPDK version. The main reason for the performance drop is that being implemented in Safe Rust, our code uses vectors to represent packet data. To create a response packet, we need to extend this vector thrice by calling extend from slice function, which checks if the vector needs to be grown and performs a copy. In contrast, the C implementation benefits from a much lighter unsafe invocation of memcopy. As an exercise, we implemented the packet serialization logic with unsafe Rust typecast that allowed us to achieve 85 to 94% of the C's performance. However, in RedLeaf, we do not allow unsafe Rust code. To evaluate the overheads introduced by transparent driver recovery, we develop a test in which RV6 program accesses the RV6 file system backed by an in-memory block device. The benchmark application continuously reads and writes files in the file system using 4K blocks. The file system accesses the block device via a shadow driver that can perform recovery of the block device in case of a crash. During the test, we trigger a crash of the block device driver every second. Automatic device driver recovery incurs a small drop in performance, 5% for read and 16% for writes. By articulating these principles of isolation, along with a practical, safe language like Rust, RedLeaf provides a collection of mechanisms for enabling fine-grained isolation by leveraging language safety. We hope it is a step forward in enabling future system architectures, which implements secure kernel extensions, fine-grained access control, transparent device driver recovery, and so on. Thank you.